So here we're dealing with hybridization. Hybridization kind of explains why certain elements can have 3 bonds around this, or 3 bonds around the central atom, 4 bonds, 5 bonds, 2 bonds, etc. And so with hybridization, there are different types of hybridization depending on the electron pairs. So for example, sp hybridization, sp has 2 electron pairs around the central atom. Then we have sp2, 3 electron pairs around central atom. Again, these can be a combination of both lone pairs and bonding pairs. sp3, 4 electron pairs. And also when you're dealing with hybridization, we count double and triple bonds as 1 electron pairs. Then we have sp3d, which has 5 electron pairs around the central atom. And finally, sp3d2, 6 electron pairs around central atom. And so what a hybrid orbital is a combination of the atomic orbitals. So sp hybrid orbital is a cross between an s and a p atomic orbital. So it has similar properties of both. So sp2 hybrid orbital has more what we call p character than s, because it comprises of 2 atomic p orbitals and 1 s atomic orbital. So when you see the sp, sp2, sp3, sp3d, these are the atomic orbitals that we take to make this hybrid orbital. So for example, sp3d includes an atomic s atomic orbital, 3 p atomic orbitals, and 1 d atomic orbital to make this orbital. Now the atomic orbitals are different energies. However, when you make the hybrid orbital, that sp3d, for example, since this is the question we're on, sp3d has 5 degenerate orbitals. When the s, p, and d are atomic orbitals, they're different energies. But when they come together to make this hybrid orbital, they have all the same energies. And this is why, for example, phosphorus can have up to 5 bonds, because it has sp3, it can have sp3d orbital. So sp3d orbitals means you have to have 5 electron pairs around the central atom. And so they have 5 electron pairs. This would have an expanded octet. So now we have to think about which elements can have an expanded octet. And like we talked about, the most common ones are this block of 9 and xenon. So again, since sp3d needs 5 electron pairs around the central atom, it means it's going to be an expanded octet. And so expanded octets deal with the row 3 and below. And that's because in energy level 3, we have a d orbital present. And so when we look at the element choices, boron is not row 3 or below. Arsenic is. So arsenic can have a sp3d hybridization. Nitrogen is on row 2. Fluorine is on row 2. I put arsenic again, but it should have been, I believe it was bromine. Should have been this one. Let's see. Copy and paste there. I think this was actually bromine. So bromine is an expanded octet because it's row 3 or below. And then beryllium would not have an expanded octet because it's row 2. And so these are the 2 elements, arsenic and bromine, that could have an sp3d hybrid orbital because they can have an expanded octet. Now in question 2, we're looking at the valence bond theory, and we want to know what's the maximum number of bonds sulfur can form. So valence bond theory, kind of a summary of what that says. The number of lone electrons that the atom has that determines the number of bonds it can form. So this is based on the lone electron. So for example, if we look at hydrogen, its electron configuration, 1s1. So hydrogen has one lone electron, it can form one bond. So that's why hydrogen forms one bond, because it has one electron. If we look at something like fluorine, let me draw the abbreviated orbital diagram. So with fluorine, it has only one lone electron. So we draw the orbital diagram of this. And so fluorine, since it only has one lone electron, can form only one bond, which is correct. We say halogens, when they're terminal atoms, forms one bond. Now if we do the same thing with sulfur, we draw the shorthand orbital diagram. We see it has two lone electrons. So according to valence bond theory, this should forms only two bonds. So according to valence bond theory, it says hydrogen should form one bond, fluorine should form one bond. You know, that's fine, that's correct, that's what we say. Halogens can only form single bonds. But when we get to sulfur, since sulfur has two lone electrons, according to valence bond theory, it should only form two bonds. However, we know that this is not correct because we've drawn Lewis structures with the sulfur atom that has 4 bonds, 5 bonds, 2 bonds, 6 bonds, etc. So that tells us the valence bond theory doesn't work well for anything besides hydrogen or halogens. And so that's where hybrid orbitals come into, or hybrid theory, help explain why sulfur can have 4, 5, 6 bonds. Carbon can have 2, 3, 4 bonds, etc. So valence bond theory fails for anything other than hydrogen or halogens. And that's why we introduce hybrid orbitals to explain why sulfur can have so many varieties of bonds. So the correct answer here is 2. So according to the valence bond model, sulfur can only form 2 bonds. So now when we're talking about carbon, we want to know what types of hybridization carbon can have. And if you remember in previous sessions, we talked about what types of geometry carbon can have as well. And so just like with geometries, there's only certain hybridizations that carbon can have. So let me first draw the different bonding motifs for carbon. So one type of bonding motif for carbon is 4 single bonds. So if carbon has 4 single bonds, it has 4 electron pairs. This would be sp3 hybrid orbitals. Whenever you see carbon with 4 single bonds, it's sp3 hybridized. Next, another bonding motif of carbon is 1 double bond and 2 single bonds. So here we have 3 electron pairs. This would be sp2 hybrid orbitals for carbon. Notice you count double bonds as 1 pair. And then the other type of bonding motif for carbon is 1 single bond, 1 triple bond, or 2 double bonds. And so here, both of these forms of carbon have 2 electron pairs. So this would be sp hybrid orbitals. So these are the only hybridizations carbon can have depending on what types of bonds surround carbon. So sp, sp2, sp3. So B here. So now we're actually going into this problem to assign hybridization of the central atom. Again, the hybridization or hybrid orbitals occurs in the central atom, not the terminal atoms. And so here we have the molecule IF3, and we want to determine the hybridization of the iodine atom in IF3. So you can draw the Lewis structure to determine the number of bonding and lone pairs of electrons, and then sum them up to get the total electron pairs. Or what you can do is that since this is a central atom bound to halogens, we can determine the total number of valence electrons, which would be 7 times 1 plus 3 times 7. It's 28 electrons. And so there's going to be 3 bonding pairs because we have 3 fluorines. And each bonding pair wants 8 electrons. So 3 times 8 is 24. So what's left is 28 minus 24 means we're going to have 4 electrons on central atom. So this is 2 lone pairs. So here we have 3 bonding pairs plus 2 lone pairs equals 5. So this would have 5 bonding pairs, or excuse me, 5 pairs of electrons. And so what you do is if you count 5, we start here, we go S, P, 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 that's 4, D. This would be sp3, D hybridization. Now, if you don't like the mathematical way, you can draw the Lewis structure. You see here, this is the Lewis structure of IF3. We have 3 bonding pairs of electrons, 2 lone pairs. Now, a neat little way to determine the hybridization. This has nothing to do with the bonds, but just a little shortcut that one of my student instructors showed students a long time ago is you can start here, go S, P, and just remember P has 3, P, P, D. And so this is sp3d hybrid orbitals for iodine. Draw that D better. This again is a shortcut. All of these bonds are sp3d hybridized, but this is just a little way of how you can go about assigning what type of hybrid orbitals are on the iodine atom. Just remember that P always has 3. So the correct answer here is sp3d. And it adds up to 5. 1s plus 3p plus 1d equals 5. So here we have BrCl5. And again, you can draw it or you can use mathematics to solve the problem. So if we use mathematics, we determine the total number of valence electrons. So this is kind of like a quick way, I guess you could say. We have 1 bromine plus 5 chlorines, total of 42 electrons. Now there are 5 chlorine atoms, so there's going to be 5 bonding pairs. So 5 times 8 equals 40 electrons for those bonding pairs. So we have 42 minus 40. There's going to be 2 lone electrons on the central atom. So this is 1 electron pair. So total number of electron pairs on the central atom, 5 plus 1 equals 6. So what you can do is you go S, that's 1, P, P, P. Now we have 4, D, D, and it's SP, 3, D2. That adds up to 6. Now if you want to draw the Lewis structure, this is what the Lewis structure looks like. So again, you can start here, go S, P, 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 D, D. So SP3, D. Again, this is just a quick way of determining the hybridization. It doesn't mean that this bond is a P bond. It just means it's just a quick way to remember hybridization. All of these bonds around the central atom have sp3d2 hybrid orbitals. So our last question deals with determining the hybridization of the elements or the atoms with numbers next to it. So again, here we look at N1. So we have a nitrogen atom. And so if you want to use the kind of the short way to do it, we go S, P, P. So this nitrogen is sp2 hybrid orbitals. Again, double bonds, triple bonds count as one pair. Next we go to this carbon here. Again, we go S. Now this carbon is attached to this hydrogen. There is a bond here, so that's P and P. Again, double bonds, triple bonds count as one. So this carbon is also sp2 hybrid orbitals. Now we go to oxygen, we have S, P, P, P. And so this would be sp3 hybrid orbitals. Next we go to sulfur. So we start here, we go S, P, P, P. It's also sp3 hybridized. Now remember, double bonds and triple bonds count as one, or one pair of electrons, I should say. So for N5, we have S, P, and then there are 2 hydrogens attached to this nitrogen, so that's 2 P's, one for each hydrogen. So this would be sp3. So this is not a coincidence. Whenever you have an organic molecule, 98% of the time, 99% of the time, you're going to have one of 3 hybridizations: sp, sp2, sp3. So whenever you have an organic molecule, like I said, for general chemistry, especially 99% of the time, you're going to have one of these 3 hybridizations for the different atoms in the organic molecule. Now, if you happen to take organic chemistry, then this may expand a little bit, but again, the majority of the time, sp, sp2, sp3 hybrid orbitals are the only types of orbitals you'll observe in organic molecules.